Hello, guys. Welcome to another episode of Good Education. Today, we are continuing our discussion of of transparency in Apple Metal. Just a quick review for those that are just seeing this series for the first time. We have an application that basically is trying to demonstrate transparency. Now we have order independent transparency, which is basically the correct way of processing transparency of all these window panes, regardless of you know when the panes were rendered, how they were rendered, the sequence of rendering, all of that. So we have order independent, which is it's processing transparency the correct way, and then we have unordered, which means you're sort of randomly dealing with the transparency, and it's based on which panes were drawn first, right? So it's sort of a chaotic unordered list or way of seeing the transparency. And as you could see, like you know the 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 transparency is randomly distributed, even though it's just randomly distributed, right? There's no rhyme or reason. It's sort of like whatever, but here it's a little bit more ordered, right? We obviously see that the green is in front, and then we have stuff behind it, right? But that's the battle that we're fighting, right? That's the battle that we're fighting, and we have to sort of discuss certain concepts for us to better understand it. Now, I am going to go. I'm going to take you guys to school again. This is we're gonna be processing. We're gonna be processing. We're gonna be talking some concepts here, but I promise you that I will touch on code a little bit more in this episode. So I know you guys like code, and I know you guys, TikTok, love TikTok, and your attention span is not all that great, but just stick with me and I will show you the way. All right. So that's the thing is diving further down into this transparency discussion in Apple Metal. Okay. So a couple of things is we have tiles, we have memory, image blocks, all of that stuff. But let me just go into the actual discussion, and we shall right we shall right. So break down exactly how. Okay, right. So here's the pipeline. Okay, so we did this before. Break down exactly how Meadows image blocks implement this, right? So there's a concept called image blocks, which we'll dive into further. So here's a pipeline Apple's sample is using. At a high level, it does not blend transparent fragments directly into the frame buffer as they arrive. This basically means that you know it does not blend each window pane color directly into the frame buffer, into sort of what is displayed on the screen as they arrive. Instead, it uses an image block as a little per tile scratch pad in on-chip tile memory. Storage each fragment's color and depth there, and then runs a tile shader that composites that. Okay, all right. Let's just pause. Okay. What happens is that when we run our application, so let's just run it again, right? Everything is the whole scene. The whole scene is broken up into tiles. Okay, so everywhere that we're seeing on the screen is broken up into little tiles. So just think of it as being like a grid of tiles. Okay, there's a grid of tiles that makes up the scene. So for you guys to pay attention, we'll pause it, right? So there's a tile here, there's a tile here, there's a tile here, there's a tile here, etc., etc., right? So everything is based on a tile, right? So this tile is obviously going to render something different than this tile, which is going to render something different than this tile. And maybe there's the tile covers both parts, so it's like here and here or whatever, right? But it's basically everything is broken up into tiles. Okay, so let's just keep that in mind. Do I want to keep this running? Okay, yeah, let's just Yeah, it's okay. All right, so it's broken up into tiles. So at a high level, it does not blend transparent fragments directly into the frame buffer as they arrive. Instead, it uses an image block as a little per tile scratch pad in on-chip tile memory. Okay, so the image block now is sort of memory associated with each tile. So remember now we have our tile, and we have our tile, and we have our tile, and then in each tile we have it uses an image block as a little per tile scratch pad in on-chip tile memory. So for each tile, we have this concept of an image block that basically, associates memory to each tile. So each tile now, each little tile has a certain amount of memory associated with it. And this is sort of a more sophisticated way of dealing with um, pixels or groups of pixels. So normally a pixel just has color and depth, right? So what is the color of this pixel here? And how far is the pixel in terms of like, whatever image or object it's associated with, how far is it away from the camera, right? With an image block concept, you have the ability to associate more information to that specific not necessarily pixel, but that specific group of pixels called those groups of pixels associated with the tile, right? So like here, if this is a tile, we do have maybe a depth value, we do have a color, but then we also can store information. So for example, we could say, okay, behind this particular window pane, what other colors are associated with this particular tile, right? And then when we have that information for what other window panes are behind this particular region, we could do some calculations, we could do some processing as a group to figure out, hey, what is going to be the color of this this region, okay? That's what all of this is saying. Instead, it uses an image block as a little per tile scratch pad in on-chip tile memory, right? So that's what that is all about. Okay, so it uses an image block as a per tile scratch pad in on-chip tile memory, stores each fragment's color and depth there, and then runs a tile shader. Shader, guys, you guys remember what shaders are? Shaders is instructions and processing on the GPU, and then runs a tile shader that composites those stored fragments in the correct order. All right. So what do we mean by that? Okay. So remember I said, let me pause it, or yeah. Okay. So remember I said that. Come on. All right, I'll do it from here. I can't, guys. Like, really, this is too. Anyway, all right. Remember, I said that each tile you could associate it with it, more information, right? So stores each fragment's color and depth there, and then runs a tile shader, GPU processing, that composites those stored fragments. So the stored fragments is all the window panes, all the colors of the window panes behind this main green window pane, right? And then runs a tile shader that composites those stored fragments in the correct order. So the problem with this example, right? The basic problem with this example is that you need to process all of these colors, especially dealing with transparency. You need to process it in the correct order so that you get the correct final result rendered to the screen, or the correct final color on the pixel that the camera is seeing. So as you can see with the unordered, it's all like random and jumbled, right? And it doesn't really make sense. Like this one is more pronounced than whatever, it's just random. But order independent, you are basically making sure that you're stacking, that you're processing the colors in the correct order so that your final color that you see represented to the camera is true and correct, right? So that is the problem that we're trying to solve here. And that's why it says, and then runs a tile shader that composites those stored fragments in the correct order. Apple describes the sample as drawing overlapping squares, storing fragment color and depth in tile memory, and then blending the stored values in back to front order. Okay, very important, back to front order. So we are doing, we're doing it from back to front order, right? That's the correct way. Apple describes the sample as drawing overlapping squares, which we see here, storing fragment color, so each one of these squares has a color associated with it, and depth. Each one of these squares has a particular depth away from the camera in tile memory, right? So tile memory now is, remember, on-chip tile memory, image block. We have a tile, we have tile memory, and it's related to the image block, all of that, right? So Apple describes the sample as drawing overlapping squares, storing fragment color. All of these squares have color, and we have to store the fragment, we have to store the color. And depth, each one of these squares has a depth associated with it to the camera. So this one is the closest, this one is the farthest over here. And then blending the stored values in back to front order, right? So we blend from back to front. And there's the equation and everything that does the blending for that particular situation, right? So we blend, we blend the colors in the correct way. Okay, so that is what this is saying. What image blocks are doing here? An image block is Apple's way of exposing a 2D data structure in tile memory. Okay, so fragment functions can access only the pixel corresponding to the fragment they're shading. Fragment functions can access only the pixel corresponding to the fragment they're shading. Okay, so basically for every, every color and fragment, whatever, it can only access that particular pixel corresponding to the fragment they're shading. While tile shaders can inspect and manipulate the whole tile's worth of data. So if we have, what it's basically saying here is that, so fragment functions can access only the pixel corresponding to the fragment they're shading. So, a fragment function is basically on a per pixel. So we have millions of pixels here. So the fragment function is on a per pixel basis, right? But while tile shaders, so we have a whole tile, right? So instead of it being millions of pixels, we have less than millions of, or an order of magnitude less number of tiles, because we're grouping the pixels into tiles. While tile shaders can inspect and manipulate the whole tile's worth of data. So we have a tile here, and the tile shader, which is instructions on the GPU side, right, can inspect. Those instructions on the GPU side can inspect the entirety of that tile, while tile shaders can inspect and manipulate the whole tile's worth of data. Apple also notes that image blocks are designed for efficient movement and layout of image-like data in tile memory. So we'll just revert back to my friend here. Apple also notes that image blocks are designed for efficient movement and layout of image-like data in tile memory, and that tile shading and fragment processing are tightly integrated with them. Apple also notes that image blocks are designed for efficient movement and layout of image-like data in tile memory. We are dealing with images after all. Image-like data in tile memory, and that tile shading and fragment processing are tightly integrated with them. One of the things that we have to keep in mind here when we're talking about this, notice that it says instead it uses an image block as a little per tile scratch pad in on-chip tile memory. This on-chip thing is very important because these things have to be processed very fast. We don't want to be going, we don't want to be going to like, to the CPU or like, the general memory or like, some distant lands where memory is stored. We want to keep things as close as possible. So we keep it on chip because we have to process these things fast, right? So Apple also notes that image blocks are designed for efficient movement and layout of image-like data in tile memory, and that tile shading and fragment processing are tightly integrated with them. Okay, so that's what this is about, right? Tile shading and image and fragment processing. So tile shading is GPU instructions and processing on the tile, related to the tile, and then fragment processing is like colors on per pixel stuff, right? For this example, that means each pixel in the tile doesn't just hold one final value, it holds a small custom record for transparency data, such as multiple transparent layers with fragment color, alpha, and depth. Okay? This is exactly what I was talking about. Okay, so again, for this sample, that means each pixel in the tile doesn't hold just one final color. It's not just, the green pane. It holds a small custom record for transparency data, such as multiple transparent layers. So these are the multiple transparent layers with fragment color, alpha, and depth. Okay? That custom per pixel storage is the key trick. That custom per pixel storage is the key trick. Okay? Let me just pause here. This image block thing is something that is, we will see it's something that's kind of special to Apple and, the way how Apple does stuff. I'm not going to go out on a limb and says no one else or nowhere else has this concept. But, I mean, we do know this image block discussion, for the most part, is proprietary to Apple. And it's actually pretty cool because, you could actually store additional information. Each pixel in the tile doesn't just hold one final color, it holds an amalgamation of color. And basically each pixel in the tile doesn't just hold one color, it could hold a whole lot more information per pixel, right? And that's something that's kind of special to the Apple ecosystem and all of that. So I just want to, that custom per pixel storage is the key trick. We'll discuss that later, but I just wanted to highlight it here. First phrase, rasterize transparent geometry, but don't finalize blending. So the app renders the transparent quads normally, but the fragment stage does something different from traditional alpha blending. Instead of reading the current frame buffer color, blending the new fragment immediately, writing the result back, instead of reading the current frame buffer color, blending the new fragment immediately, writing the result back, the fragment shader writes that fragment's attributes into the image block entry for that pixel. Since fragment functions only access their own pixel location in the image block, each fragment contributes into the per pixel transparency structure for its screen position. Okay? This is exactly the kind of per pixel custom data structure Apple says image blocks enable. So basically, again, you could develop a data structure per pixel. You could store information. You could do all kind of crazy stuff per pixel, and this is pretty cool. They wrap it into this concept of the image blocks and all of that stuff, right? Fragment functions only access their own pixel location. So we have a tile, but that tile has thousands or millions of pixels. But the fragment function can only access that its own particular pixel in the image block. Each fragment contributes into the per pixel transparency structure for its screen position. So yeah, it just basically the fragment contributes, the tile is made up of many pixels, but the fragment, just contributes per pixel, right? This is exactly the kind of per pixel custom data structure Apple says image blocks enable. So, the image blocks can now look at all this data, look at all the, not only just the pixels in there, but also the data associated with each pixel from the fragment functions and all of that stuff, right? So it's like a cascading, level of detail kind of thing. You have the tile, you have the millions of pixels in the tile, you have the fragment functions that like are accessing and doing stuff only with that pixel in the tile, but then you have the image block now that has all kinds of information, like the layers and stuff associated with, that particular pixel. This is exactly the kind of per pixel custom data structure Apple says image blocks enable. So after all transparent geometry has been rasterized for a tile, the tile memory contains in effect 4 pixel in coordinate XY. Here are the transparent fragments that hit it, right? So what it's saying is that for the particular pixel, all right, so for the particular pixel, let's read it. Here are the transparent fragments that hit it. So for a particular pixel, what are the other transparent fragments that sort of, affect this particular pixel right here, right? And we see that we have other stuff going on, in the background, right? For this particular pixel, or maybe this particular pixel over here, right? That's what that's saying. Why tile memory matters, okay? So this storage happens in tile memory, which is on chip and high bandwidth. Remember I said we would discuss this concept some more. Why tile memory matters. This storage happens in tile memory, which is on chip and high bandwidth. Apple's tile shading docs explain that doing this work inside a single render pass avoids repeatedly spilling render data out to device memory and reading it back for a later compute pass, right? So again, on chip and high bandwidth, okay? So we're holding this information close to the chest. We're not going to device memory. We're certainly not going to the CPU. We're not going to your grandmother's house. We're not going to your family reunion or anything like that. We are staying on chip and high bandwidth. Okay? We're staying on chip and high bandwidth. Apple's tile shading docs explain that doing this work inside a single render pass avoids repeatedly spilling render data out to device memory and reading it back for a later compute pass, right? Because if we got to go to, your distant family's house, and store the data there. In order for us to retrieve that data, we got to go back over to that house, and we don't want to do that because it takes time, latency, right? It takes time to do that. So we're keeping on chip and high bandwidth, right? Apple's tile sharing docs explain that doing this work inside a single render pass avoids repeatedly spilling render data out to device memory and reading it back for a later compute pass. This is the performance reason the sample uses image blocks and tile shaders together. Okay, so pretty cool stuff. Apple is always interested in performance advantages and performance gains and stuff. The sample uses image blocks and tile shaders together, okay? So the sample is not just order independent transparency in theory. It is demonstrating how to do OIT in a way that fits Apple GPU's tile-based architecture. Okay, so tile shader, second phase is tile shader resolves transparency. So first phase, rasterize transparent geometry, don't finalize blending, right? That was the first phase. Second phase, tile shader resolves the transparency, which is basically it's doing like the finalizing the blending and stuff, right? So after the fragments for a tile are collected, a tile shader runs. Now remember, guys, when we say shader, we're talking about GPU processing, GPU instructions on the GPU. You know, this is stuff that GPU is supposed to run. So after the fragments for a tile are collected, right? So that's all the different window panes and their colors and stuff. A tile shader runs. A tile shader can inspect the whole tile's image block contents, unlike a fragment shader, which only sees one pixel. So remember we said the fragment shader and the fragment functions and the fragment processing can only see its own pixel. But a tile shader can inspect the whole tile's image block content. So remember we have a tile that is made up of millions of pixels, but the fragment shader and the fragment functions and the fragment processing can only deal with the per pixel stuff. However, the tile shader, which is basically instructions on the GPU that's dealing with, processing an entire tile. A tile shader can inspect the whole tile's image block contents, which means all the data and information, not only for each pixel, but for all the pixels in the tile. Apple describes tile shading as a programmable stage that can analyze image block contents, summarize them, and operate directly on tile memory inside the render pass. So it's a programmable stage that can analyze image block contents, summarize them, and operate directly on tile memory inside the render pass. Okay, so we kind of get that. Right, so it can analyze the whole tile, summarize them, and operate directly on the tile memory inside the render pass. So this is us now trying to resolve, okay, what is the final color that we're gonna basically render to the screen for this particular pixel. Now, we're not saying that the entire tile has one color. We're just saying that, each pixel in the tile is being resolved, based on its own particular information. So it's not like, at least I don't believe that we're trying to determine for the entire tile one color. We're saying, okay, we have a tile, we have a body of work, we have some information, we have a section, a region of information. Okay, for each pixel in this tile, what is the color gonna be, right? Because let's say you had a tile that like spanned multiple regions in the scene. You can't expect that tile to just be one color. It could be, it could have multiple striations of color inside of the tile. Okay, in this sample, the tile shader's job is roughly for each pixel in the tile, gather the stored transparent fragments, right? So okay, what are all the colors that add up, to this pixel or this dot or region inside of the tile? Order those fragments by depth, right? So we're doing, we're trying to figure out for these fragments now, for these window panes, what's the depth of these window panes? So, right. So for each pixel, gather the stored transparent fragments. So what are all the window panes that are affecting this pixel? Order those fragments by depth. So what is for each window pane, what's the depth of that window pane, right? Composite them back to front. So remember I said we're processing from back to front. Write the resolved final color out as the pixel result. So yeah, we're writing the resolved final color out as a pixel result. Okay? That store first, blend later structure is what makes it order independent with respect to draw order, right? So this is where this order independent thing comes in, because we are trying to basically we're trying to not have the final color be whatever was drawn first and whatever is just splashed on the screen whenever, right? We're trying to do this in a structured, ordered, and accurate manner so that we get a true transparency and something that is believable. That store first, blend later structure is what makes order independent with respect to draw order, right? Why this becomes order independent. With ordinary transparency, the result depends on which fragments get blended first. If you render near to far instead of far to near, you get a different image, right? So if you switch up the ordering of what you're rendering and you don't have you don't enforce the back to front rules, you're going to get a different image and you're going to get a different result, right? And we see that when we go here, right? We get a different thing, and it's not coherent. It doesn't necessarily make sense. It's just like whatever was splashed on the screen. But here we get something that's a little bit more sensical, right? So that's that. In Apple's sample, draw order no longer decides the final answer because draw order only affects the order in which the fragments are collected, not the order in which they are composited. Okay, all right. We're doing some word math here, right? So draw order only affects what fragments are collected, the order in which the fragments are collected, not the order in which they are composited, right? Which basically means you could give me the farthest window pane first, and then the second to nearest one next, and whatever. I don't care what order you give me, right? I'm gonna make sure that when I do my blending, when I do my final result, that first I order all of the panes based on depth, right? Because remember, we're doing from back to front, right? So again, in Apple's sample, draw order no longer decides the final answer because draw order only affects the order in which fragments are collected, not the order in which they are composited. The actual compositing happens later from the stored depth color data, right? So remember, depth and color data using the correct depth ordering. Apple's sample summary explicitly says it stores fragment color and depth and then blends in back to front order, okay? So there you go, guys. So the order of the submission is irrelevant. The order of resolve is what matters, right? The order of resolve. So we're doing back to front, right? Why Apple calls the other mode unordered transparency. That mode is basically the control case. The fragments are allowed to blend in whatever order rasterization produces them. No per pixel storage, no later sort resolve. So it's cheaper, it's simpler, but the output is visually wrong for overlapping transparency, which we see, right? When we do the unordered transparency, it's just like random stuff, right? The order independent transparency mode adds the image block storage, right? Which is like, yeah, per pixel, storage and order and depth and color and stuff. And the tile shader resolve step. So we actually have to collect all that information and, sort the panes back to front, farthest to closest, and then decide what the final step is based on equations and math and stuff. So that the final result is the final color, so that the blending order is reconstructed correctly. The OIT, the order independent transparency mode, adds the image block storage and the tile shader resolve step, so the blending order is reconstructed correctly. Important nuance. This is a bounded per pixel method. Okay, so this we're gonna get into some more nuance here. This kind of image block order independent transparency usually stores only a limited number of layers per pixel. So we don't have infinite memory. I don't care how expensive your machine is. This kind of image block order independent transparency usually stores only a limited number of layers per pixel because tile memory is finite. I don't care how much money you put down on whatever options you tick off on your machine. It's still finite. Apple's image block tile shading talks frame this as using custom per pixel structures in tile memory for techniques such as approximate order independent transparency / multi-layer alpha blending. All right, I mean basically guys, like, yeah, it's finite memory. Like we don't have infinite number of layers that we could store per pixel, right? This stuff is, remember guys, we said on chip and high bandwidth. So, you know, we're dealing with very close to, you know, very close to the processing, but you know, because it's so close, we don't have infinite amount of memory. Now, if you want to go store the stuff in your external hard drive over in Timbuktu, that's your business, okay? But just understand, you're gonna get a performance hit because now, you know, we're gonna go back to Timbuktu to retrieve the data so that, you know, you can resolve properly what the whatever is, right? So conceptually it is keep several nearest, farthest, relevant, transparent fragments per pixel, resolve those layers correctly later. That is different from a theoretically unbounded per pixel linked list method on desktop GPUs. Apple sample is built around what fits efficiently in tile memory. All I can say is like, I believe this. I think this example can run. I know. I mean, obviously it runs on Mac OS, but I don't know if it can run on like iOS or Vision OS. But yeah, there's some to this. Like, you know, this example I don't think can run on every piece of Apple hardware. I mean, obviously it has to be Apple Metal capable, but I don't know if it could run on every iteration of hardware. So you have Mac OS, iOS, Vision OS. Which other OS is there? I don't know. But yeah, you know, there are limitations to it because of that. You can think of it as two passes, mental model for the whole sample. You can think of it as two passes inside of one render workflow. Collection pass, transparent quads are rasterized. Each fragment stores depth, color, and alpha into an image block structure for its pixel. Resolve the pass. Tile shader reads the stored layers for each pixel, sorts them by depth, right, back to front, blends back to front, right, and outputs the final transparent result. That is the exact architectural idea the sample is demonstrating, and it matches Apple's description of image blocks as custom per pixel tile memory storage, and tile shaders are as the stage that can analyze and reduce that per pixel data. Right, so when it says analyze and reduce, basically you're taking that information of all the layers and everything, and then you're coming down to a final color. Right, you're reducing to a final color and then displaying to the screen. Okay. Can I transfer this to codecs? No, you can't transfer to codecs. Blah blah blah. We don't care about that. I will go to codecs though. Codecs is for you guys that don't know. Codecs is sort of it's the programming platform. So you have ChatGPT, which is like general knowledge and everything, but Codecs is what lives in Xcode. So Xcode is the GUI that you program Apple stuff in. It's it's like the Visual Studio for Mac OS. So Codecs, the reason why you'd want to do stuff in Codecs is because Codecs is aware of all your entire application, all the files associated with your application. So you can ask it questions that directly deal with your code. I can't upload all the files for the project into ChatGPT. It just gets wonky and it's too many files, and there's like a size limit and a file number limit, and like I even tried to zip the files and give it to ChatGPT, and It just doesn't work. So you want to do it inside of your application, when you're programming your application. So that's what Codex is for, and that's why I was trying to do it into Codex, blah blah blah. Yeah, but I was able to transfer it anyway. We'll get to that. Okay, so what is an image block? Is it proprietary to Apple? So remember I said I will get back to, the image block stuff and whatever. An image block in Metal is a very specific GPU concept. And yes, it's essentially Apple specific, at least in the way Apple exposes it. Let's break it down cleanly. What an image block actually is. An image block is a custom per pixel data structure stored in tile memory, accessible during rendering. So this is a huge innovation. Instead of thinking of a pixel as just color and depth, so color and how far away is it from the camera, you can think of it as your own structure per pixel, your own struct per pixel. So you could, you could store a variety of data. And this right here is a exact reason why, guys, I do what I do. Is because for you creative people out there, that's going to create the next Disney, the next Pixar, the next DreamWorks, the next, I don't know, what other studio is out there? Whatever, the next whatever, right? Custom, your own struct per pixel. So you could do custom things that the world has never seen before. And all I ask is, when you make it, I want a yacht, and I want a private jet, and I want an annual budget. That's all I ask: a yacht, a private jet, and an annual budget. Okay, and of course all the fees that are associated with the yacht and a jet annually. Okay, because that's all I ask. But again, guys, per pixel. Your own strut per pixel, right? So you could customize this stuff and make something that the world has never seen before, right? So that's why I encourage you creative people to get involved in this stuff. I know it's not, what you would typically think is part of your wheelhouse, but once you get through the hard stuff, it becomes very, the world opens up to you. I personally am not that particularly creative, but I think I'm good at teaching, so that's what I do. All right, so your own struct per pixel. Your own struct per pixel. For example, in the order independent sample, a pixel might store fragment count, depth, and color. Okay, so whatever. Where it lives. Image blocks live in. Now, just so you know, guys, again, I'm in ChatGPT, so it's not fully aware of the intricacies of the example. I mean, I did reference the application page and stuff, but so it's gonna kind of just fumble through it and just make stuff up to sort of teach us what we're trying to get at. Okay, image blocks live in tile memory, on-chip GPU memory, right? So we know this because we're trying to do stuff fast. Apple GPUs are tile-based deferred renderers, which means the screen is divided into tiles. Example 32 by 32, pixels. Each tile is processed entirely on chip. Results are written to main memory only at the end, right? So this is what we want. We want the tiles and all the processing to be done, very fast, so it's on chip, and then we just spit out the final result to memory, right? So an image block is allocated per tile, indexed per pixel within that tile, extremely fast, no external memory bandwidth. So again, this is the whole, we're not going to your grandmother's house to store this stuff. We are doing it on chip, very fast. Who can access it? Fragment shaders can read write only their own pixel entry, right? So fragment shaders. So shaders again is GPU instructions on the GPU to do stuff, but like the fragment shader and stuff is like it can only see its own pixel. Used to store per fragment data. We'll leave that alone. Tile shaders, Apple specific stage, right? So can access the entire tile's image block used to inspect all pixels, right? So remember, we have a group of pixels that make up the tile. Sort, reduce, or combine data. Sort, reduce, or combine data, and produce final output, okay? So again, the tile shader is seeing the whole tile, all of those pixels, and then it's doing stuff based on, its ability to see and access and read all the pixels in that tile. Why image blocks exist? They let you do things that are impossible or inefficient with normal rendering. Examples: order independent transparency, your case, custom blending pipelines, deferred shading without G buffers in VRAM. VRAM, I think, is like, yeah, it's GPU memory. Per pixel data structures, lists, arrays, accumulators. Yeah. I might have did this in the advanced rendering because I know the lights are lists. But maybe that's different. Okay. How this differs from normal rendering. Traditional pipeline, fragment shader, blend, fragment frame buffer in VRAM. With image blocks, fragment shader, write to image block, tile memory. Tile shader, process all stored data, final color, written out, right? So we kind of followed this timeline and it makes sense. So instead of blend as you go, you get store everything, then decide later. Is this proprietary to Apple? Yes. In this exact form, image blocks plus tile shaders are part of Metal, designed around Apple GPU architecture. Now, not to digress, but Metal is a successor or is a child of it's not the only child, but it's a child of Mantle, which was created by AMD. So Mantle is like the godfather of computer graphics, and it is what Metal on, for Apple's purposes and Apple's side is what Metal is based on, and then for the rest of the world, it's where OpenGL and Vulkan and stuff is also based on. So they both have the same grandfather, right? But this is the route that Apple decided to go. Image blocks and tile shaders are part of Metal, designed around Apple GPU architecture. So remember, Apple is vertically integrated, so they have everything. The GUI, the computer, the software, the GPU, the CPU, the memory, whatever. It's all decided by Apple, okay? Other APIs don't expose this model directly. Closest equivalents elsewhere. So in Vulkan, you have the subclasses plus independent input attachments, tile local behavior on mobile GPUs, but no custom per pixel structs like image blocks, less flexible. I can't vouch for this stuff. I don't know, guys, honestly. This is just what, ChatGPT is telling me, but whatever. And then you have OpenGL, ES, mobile, all of this stuff. And then you have DirectX 12, which is the Microsoft stuff, desktop stuff. Much higher bandwidth. Okay, so key intuition. Image blocks are basically programmable per pixel scratchpad memory that lives inside the tile while rendering. That's the mental. Why Apple exposes this? Because their GPUs already have fast tile memory, already process tiles independently. So Metal gives you direct control over it. Higher performance, fewer memory round trips, and new rendering techniques like this order independent transparency dimmer, okay? Trade-offs. So the pros is extremely fast on chip, enables advanced techniques, and no VRAM bandwidth costs during accumulation. Yeah, because it's on chip, you're not going out to the general device memory, GPU memory and all that. Cons: limited size. Tile memory is small. So remember, we touched on that, guys, right? Like, we don't have infinite memory on the on-chip stuff. Apple only API requires tile shader stage. Non-portable. One-line summary. An image block is a per pixel data structure stored in on-chip tile memory that lets you defer and customize how fragments are combined. Something unique to Metal's tile-based architecture. And then we get into some other stuff, but like I'm gonna want to transfer over now to I'm gonna transfer now over to I could close this for now. We're gonna transfer over to codecs. and we are going to do that. So just give me 1 second. Okay. All right. So we're transferring now over to Codex. Okay. So we're in Codex, and we are in Codex, and basically this is my application here. And right. So like I said, guys, Codex now, which is this guy right here, Codex now gives me full application awareness, right? So, when I run the application, I'm running it from here, but it has access to all the files and everything. So let's just go through this piece of it. I know this video is long, and it's a lot of things that we're doing in once. I was thinking of breaking this up into a second video, but I don't want to do that because I just don't want to have to reorient myself. So let's just hammer this out and be done with it. Where are the image block used in this application? Image blocks are used in two main places. So we have in the shaders, right? So the shaders, of course, is the like the tile shader and stuff, like the GPU processing instructions and stuff. And we also use it in just the renderer, the general renderer thing, right? So yeah, okay. And we just want to, transparent, yeah, I don't really want to get into this particular part of it right now. Transparent fragment value stores per pixel transparent fragment colors and depths, right? Transparent fragment store marks that storage with image block data. Init transparent fragment store initializes the image block using image block and thread group, right? Process transparent fragment writes transparent fragments into the image block. Blend fragments reads the image block and blends the stored fragments back to front, right? So this is where we're talking about, that sort of stuff. But that wasn't what I was eager to get into right now. Maybe I'll get into it after I'm done with the part that I want to focus on. Okay, so we have the AAPL renderer. Optimized tile size controls the tile dimensions for image block use. Lines 200 to 258 create the pipelines that use image blocks and tile shaders. So let us just go all the way up to 200. So we'll see here. Optimal tile size controls tile dimensions for image block use. All right, so only use transparency effects if the device supports tile shaders and image blocks. Okay, so this is where I was telling you guys, like, I'm not sure if this example can run on every device. So it can run on Mac OS, MacBooks and stuff, but Mac desktops and laptops and stuff, but it can't run on. Only use transparent effects if the device supports tile shaders and image blocks. So we see here we have, it's checking if it's supported, and then enable order independent transparency, yes. And then, we go through the whole, so 200 to 255. So we're basically at 200 here, and we go to 255. But before we even jump to that, let us make sure we have some context of where we are. So we are in the renderer file, which is like the main file that deals with rendering stuff, and that would basically mean metal, right? So we're at line 200, but this is part of the load metal function, which is up here. Creates a metal render state object, right? So we are in the load metal function. And then we go to line 200, where we're starting to talk, only use transparent effects if the device supports tile shaders and image blocks. So that's this if statement here. And then if we do it, whatever. I did try tinkering with this, putting it to no, but like, whatever. It didn't do what I expected it to do. But anyway, so we check to see if it's if it supports tile shaders and image blocks. Now, what I want to know, keep your eye on this particular region, this line right here. This is an if statement. So if it doesn't support it, then we basically go to the else, which is down here, right? So the else is down here, and we basically say it's no. Okay. And yeah, so that you guys know, we have to make sure that the device that we're running on, do we have the capability to do this? Okay. Creates a pipeline that uses image blocks, and so line 290, 295, configure the render pass with tile width, tile height, and image block sample length. So this is gonna give us some important notes when we go down there. So 290 to 295, okay? Set the tile size for the fragment shader. So we have tile width, we have tile height, and image block sample length, right? Set the image block's memory size, right? So again, guys, we don't have infinite memory. So we can't just like, make this thing as big as possible. And actually, there is some comments in this code that actually talks about that specifically. Was it in this code? It is in this code, but maybe it's the next set of lines. Okay, all right. But yeah, but this is what does the tile. This is what sets the tile, dimensions and image block sample length. Set the image block's memory size. Okay. So So we have the tile dimensions and then the memory size, okay? Tile dimensions and then what width and height, but then we also have the memory size, okay? Let's go to 483. So 483, initialize the image block each frame with init image block pipeline and dispatch threads per tile. We're not gonna get too deep into this today, of course, guys, but we just want to at least, touch on it so that we could start thinking about what exactly is going on. Okay, right. Initialize the image block's memory before rendering. So init image block pipeline, and then dispatch threads per tile, optimal tile size. Okay. And then lines 489 to 497, draw opaque objects, draw transparent objects into the image block, then run the blend pass. So from 489 to 497, so all of this stuff here. Draw opaque object, draw transparent, and then run the the blend pass, which is all this right here, okay? But I want to search for the notes. Because there is initialize the image block's memory before rendering. Okay, but there is something where it talks about just there's probably a maybe it's in the shader file. So I think we just need to go to the shader. So if we go shaders, APL shaders. No, it's not here. I could have swore, guys. Okay, here we go. Here we see. We just needed to scroll some more. Okay, all right. So this is gonna be our final discussion here. Okay, to use an image block, you must balance the fragment shader's tile dimensions, tile height, and tile width with the image block's memory size, image block sample length. Okay, there we go. A larger tile width and tile height may yield better performance because the GPU needs to switch between fewer tiles to render the screen. However, a large tile size means that image block sample length must be smaller. The number of layers the image block structure supports affects the size of image block sample length. It's kind of, an intellectual gotcha, but basically, if your tiles are huge, then you have many pixels in that tile, which means you have many layers for each of those many pixels that you have to save. And right, so if you have a huge tile, a large tile size means that image block sample length must be smaller. So maybe you can't save as many layers per pixel because you don't have that much memory. The number of layers that the image block structure supports affects the size of image block sample length. I don't want to get into the nuance of what's the difference between image block sample length and the image block structure itself, but just follow my drift here. More layers means you must decrease the fragment shader's tile size. This chooses the values to which the renderer sets tile height and tile width. So optimal tile size is this guy right here, which that's a topic for another day. Okay, but let's go over it again and kind of just see if we really understand what's going on. To use an image block, you must balance the fragment shader's tile dimensions, which is tile height and tile width, with the image block's memory size, image block sample length. Let's do it again. To use an image block, you must balance the fragment shader's tile dimensions with the image block's memory size. All right? So you're dealing with constraints here, guys. It's not just a free-for-all. To use an image block, you must balance the fragment shader's tile dimensions with the image block's memory size. A larger, tile dimension may yield better performance because the GPU needs to switch between fewer tiles to render the screen. So basically, if this is your screen, if you have very small tiles, you're gonna have to be switching between many very small tiles. But if you have a big tile like this, 1 tile, 2 tile, 3 tile, 4 tile, then it's less switching, right? But you have to balance the two. Less switching, but then you have other constraints. A larger tile dimension may yield better performance because the GPU needs to switch between fewer tiles to render the screen. However, a large tile size means that image block sample length must be smaller. The number of layers that the image block structure supports affects the size of image block sample length. Okay? More layers means you must decrease the fragment shader's tile size. So if for each pixel you're trying to save a million layers, you're not going to be able to have many pixels per tile, right? Because it's a lot of, for each pixel, it's a lot of memory that you're, it's a lot of heavy bag. You have personal, you have carry-on luggage, you have personal item, and you have check bag, okay, for each pixel, right? So you're going to have to make your tile size smaller. But if you just have personal item for each pixel, like one layer or whatever, then you could make your tiles a lot bigger, right? This chooses the values to which the renderer sets tile height and tile width, right? So there you go, guys. All right, and that's where sort of I conclude this discussion here. So hope you guys learned something. Let's just do a quick peruse of the shader. So remember, the shader now is like GPU instructions and stuff like that and whatever. But I'm just gonna do a run through. I'm not even gonna talk much because we've done a lot. Yeah, we've done a lot, guys. Anyway, guys, computer graphics is the gift that keeps on giving. There's no end in sight with this stuff. But again, guys, if you create the next Pixar or DreamWorks, or even like a oh man, I can't even, anyway. Yeah, just make sure. I want, you guys gonna have to pay me back. All right, you're gonna have to pay me back. And don't worry, I have ways of finding out if you benefited from my stuff. Okay, so don't think you can hide. I'm just playing. All right, guys. This is CUDA Education. I will link the example code down below. And yeah, just check out, support the channel. You guys know what to do. It takes a lot of time and effort to create this stuff, to make this stuff. So, please help out any which way you can. Like, subscribe, share, tell your friends. Be a leader in your community. Encourage people to start on their Apple Metal journey. Lots of devices out there, guys, that's running Apple Metal. Lots of Apple devices out there. So, whether you want to do a Vision OS stuff, a Vision Pro, whether you want to do an Apple Watch something, or like an iPhone app, or something that runs on Mac OS on the desktop, this is a good starting point. Even if you want to do AI, because remember, Metal is interfacing with the GPU, which means you could do like parallel processing and inferencing and all that stuff. So you can't lose learning this stuff. You can't lose learning this stuff, especially in 2026. So thank you guys for watching. Have a great day, and I'll see you again.